dash mu 2 sigma 2 and etc. This is my x direction, this is my z direction. So what will be the y direction? It will be towards the screen or away from the screen? Towards the screen. Just one second.
Away from this.
Next one second. Okay. X, y will be, just check. If we move from x to y, it will be like this. So this y will be like this. Okay. This is the y. So we have the EM wave in phasor notations. E incident wave as a function of x, that is E0 to the power of minus j beta 1 x. This is my incident wave, that is towards this boundary. Okay. When the wave reaches the boundary, a part of it propagates. Okay. Let us give that E transmitted x, that is E1 e to the power of minus j beta 2x. Why beta 2 here? Why it is beta 2 here?
That beta equal to 2 pi by lambda, and lambda depends on the
On the main property.
lambda depends
So if the
on
properties change, obviously lambda will change. So that's why here the beta will be different. And apart it reflected by ER x, that is E2 e to the power of plus j beta 1 x. Why plus here? This will be this will be along z direction. This will be along z direction, and this will be along z direction. Because the wave is propagating in plus x direction, the electric field is in along plus z, and the magnetic field is along plus y. That's what we had seen. Okay, Devendita Ghosh is probably in our class. Is it okay? And for magnetic field, it will be, this one will be Hix equal to E0 by eta 1 to the power minus j beta 1 x g. This will be H reflected, that will be E2 by eta 1 to the power of j beta x g, and Et x equal to by eta 2 . Here it is a negative sign. Right?
Sir, what is written in the second line of the right hand side?
Okay, there is one connection. This will be along J and this will be along K. Otherwise, it is along. Because J dot K is I. Okay. So why there is a negative sign here? Why there is a negative sign in that A chart? Here there is a negative sign. There is no negative sign otherwise. Why there is a negative sign here? Why there is a negative sign? This is because this wave is propagating along the minus I direction. That is why it is along minus K. Because J dot K is I. So J dot minus K will be minus. Is it okay? Why there is minus K? This is there to ensure that the wave is propagating along minus I. Because I, J, K. So cross this, then J cross K is I and K cross I is J. So if the wave has to propagate in the minus I direction and the electric field is along plus J direction, then the magnetic field will be along minus I. That is why it is minus. Is it okay? Is it okay? Are you there? Is it okay? Why there is minus sign here? Okay. Now, in order to find out E1 and E2 in terms of E and eta 1 and eta 2, we need to apply some boundary conditions. So, let us see what the boundary conditions are. Suppose I have a boundary of 2 mediums. Okay. And we take here a very small area. The length is, it's a rectangle. The length is L and the breadth is W. So, area would be delta A would be L times delta W. And since delta W tends to 0, delta A should also tend to 0. Correct? Is it okay? Now, also, let us consider the electric field vector. This is ET1. This is ET2. This is, sorry, EN2. Sorry, EN1A. This is EN1B. This is EN2B. This is EN2A. And finally, this is ET. T is a tangential direction and N is a normal direction. Is it okay? So, do you understand the directions of the fields? Now we apply the Faraday's law in integral form, which says that closed integral of E dl, that is minus del del t of V ds This we had seen. This we had seen for Faraday's law. Is it okay?
Yes, sir.
But what is ds? ds is here L delta W delta N or N cap. Since this is tending to 0, ds should also tend to 0. Since delta W is very, very small, ds will also be very, very small. The area will be very small. Right? Is it okay?
Yes, sir.
So obviously due to this is 0. So this entire RHS is 0. Because ds is very small. Okay. The area is very small, so this will be 0. So we have now here closed loop integral of E dl equal to 0. Now let us see this E dl little bit here. This is equal to Et1 times L minus E N1 E times delta W by 2 plus E N2A delta W by 2 minus Et2 L minus E N2 B delta W by 2 plus E N1 N2A, sorry, N1B delta W by 2, that is 0. Is this okay? This is okay?
How we are getting the direction?
Direction we are assuming, direction we are taking is always the normal is perpendicular to the plane outside of it. Or you can take any other, doesn't matter. The normal dictate doesn't matter. Or you can take it in any other direction, no problem. The result will always be the same. Okay? I am taking it upwards. To take it downwards, you will see the result, the final result doesn't matter. Okay?
Okay, sir.
Or even you can take one upwards, one downwards, you will find the result is always consistent. No problem. Okay? Now delta W tends to 0. So this delta W terms will be 0. Delta W is very small, so the terms with delta W, they will be 0. So delta W tending to 0. Is it okay?
Yes, sir.
So what do we have? The terms without delta W, that is Et1 L minus Et2 L, that is 0, or Et1 equal to. Is it okay?
Yes, sir.
So for any boundary, the tangential component of the electric field is continuous. The electric field component just outside and just inside the boundary, the tangential component will be the same. Is it okay? But we have not said anything about the normal components. We don't even have. Is it okay?
For any boundary?
For any boundary, yes, for any boundary, the electric field component just inside and just outside will be the same. This is the boundary. This electric field, tangential field here and here, they will be the same. Okay, just outside and just inside. I am not saying that this here and this here will be the same. They may not be the same, but on the surface they will be the same. Is it okay? Is it okay?
Yes, sir.
Right. Now, what about the normal components? Same idea. We take this time. We take a cylinder. Okay. The cylinder, the the flat surface area is delta S. Okay. This is my dn1. This is my dn2. This is also delta s. Okay, and so if we apply Gauss's law, then d ds, that is equal to q enclosed. Okay, this one Gauss's law. So dn1 delta s minus dn2 delta s, that is sigma delta s, where sigma is the surface charge density of this surface. Is it okay? Why we are not taking the curved surface? Because for the curved surface, the d vector and the normal vector are perpendicular. So their d dot ds will be 0. Okay. Had we taken the curved surface here, the n vector is perpendicular to d vector. So n dot d would be 0. So we are not taking that into account. This will be the case. Or dn1 minus dn2 equal to sigma. If sigma is 0, if there is no charge density in the surface, if, which is the case most of the time, if sigma is 0 or no charge is present on the surface, then dn1 equal to dn2 or epsilon en1 epsilon 1 equal to epsilon 2 dn2. Any questions regarding this? So if there is no charge on the surface, the normal components of the electric flux density vector is continuous, not the electric field. Any questions regarding this? Any questions regarding this? Anything to ask? Any doubts?
Sir, one question.
Hmm? Tell me.
Hello.
Yes, yes, I can hear you. Tell me.
Sir, if electric field,
I can't get you. Arpit, can you type your question? I cannot hear you. Anybody else? By meanwhile, as he types, anybody else? Any questions? Anybody else, any doubts? You can type your question. Anybody else? Any questions? Is it okay? Usually for the surfaces we will consider the sigma is 0. Okay, so we can apply without any hesitation that D one equal to D. But careful that it is with D, not with T. So the E1, En1 equal to En2 is not generally correct unless the epsilons of the surface are the same. Okay. Any other question? Anybody else? Let us do the same for magnetic field. The normal component of magnetic field H, the tangential HT1, HT2. Okay. We take this the same thing we apply. This is L, this is delta W. So integral H dl equal to I enclosed equal to J dl, right? But the area of the surface is very small, so this dA is very small, so this will be 0, right? And applying the same logic what we did for electric field, we can say that HT1 equal to HT. Is it okay? Just like the electric field, the tangential component of the magnetic field is continuous across the surface. Okay. Soumya, or should I accept him? He is in the class, I believe. Okay, let's accept him. This is okay? This is okay? And finally, with the tangent normal component, Arpit, you type your question if you are, because I couldn't get it. This is B1, this is B2, the area is delta S. Okay. We apply Gauss's law for magnetism, V ds equal to 0. This is always true. So B1 delta S minus B2 delta S, that is 0, or B1 equal to B2. This implies mu1 H1 equal to mu2 H2. So any questions? So the normal components of the flux densities are continuous and the tangential component of the fields are continuous. Remember this. Any question? Any questions? So we come back to the original question what we had. E incident as a function of x is a phasor that was E0 e to the power of minus j beta x, j beta 1 x along j direction. E reflected x phasor that was E2 e to the power of minus plus j j beta 2x. Ganesh is also in the class, I think. Next, J and E transmitted is E1 to the power of minus J beta 2x G. This we know. This is our coordinate systems. This is our x, this is our z, and this is our y. What about the magnetic field? H incident x, that is E0 by beta 1 e to the power of minus j beta 1 x p. H transmitted as a function of x, E1 beta 2 j beta 2 x k, and this one any questions regarding this? Are they okay? We take that the constitutive properties here are mu1, sigma 1, epsilon 1. Here it is. Here they are mu2, sigma 2, and epsilon 2. Any questions so far? Is it okay? Is it okay? Now our target is to find E1, E2 in terms of E0, beta 1 and beta 2. Okay. So we have seen four properties that two of them are the fields are continuous, tangential components of the fields are continuous, and the normal components of the flux density are continuous. We assume that on the surface there is no charge. Okay. So we can easily apply dn1 equal to d. So which laws should be used? Which law we should apply? We assume that here on the surface x is 0. Okay, the surface is the yz, x is 0. So which things we should apply? What we should apply? The electric and the magnetic fields, they are normal to the surface or tangential to the surface?
Normal to the surface.
Why?
Electric field. Electric field.
Electric
If
field is
it's
along. Electric field is along the y direction. Okay, and the plane is yz plane. So it will be normal or tangential?
tangential.
Tangential. So that the tangential component of electric field is continuous. We have seen that. So we can write E incident 0 plus E transmitted, E reflected 0 equal to E transmitted 0. Can we write this?
Yes, sir.
Okay. So we put the values E0 to the power of minus j beta 0 plus E1, is E2 e to the power of j beta 0, that is equal to E1 e to the power of beta 1 minus j beta 0, or E0 plus E2 equal to.
Sir, incident plus reflected equal to transmitted, or incident equal to transmitted plus reflected?
That's a very good question. See here, incident is on the material 1 or material 2? This is material 1. Simran, should we have with him? Ishida? Okay. This is left we have the material 1 with mu1 sigma 1 epsilon 1. On right we have material 2 mu2 epsilon sigma 2 epsilon. Okay. So the incident wave is in material 1. The reflected wave is also in material 1. The transmitted wave is in the material 2. Right. And what we have seen that the tangential component of E in the material 1 and the tangential component of E on material 2 along the surface, along the intersection surface is continuous. Okay. As a result, so we will take it in terms of the what where we are seeing it. That is why it is EI plus ER equal to. Is it okay?
Sir.
We are not considering energy. If you are considering energy, yes, then you may say that the energy of the incident wave is equal to the energy of the reflected and transmitted. Okay, had the everything been lossless, then you can say that. We are not considering the energies. Is it okay? And if we take magnetic field, same thing. HI 0, HR 0, HT 0. Let's input our numbers. Can we write this? Can we write this? Is it okay? Is it okay?
Yes, sir.
So we can simply this we can write as E0 minus E2 equal to eta 1 by eta 2 times E1. Okay. And we can add this, we can add. So E2 gets cancelled, 2 E0 equal to E1 1 plus eta 1 by eta 2, or E1 equal to 2 eta 2 E0 by eta 1 plus eta 2. Or E1 is also plus E1 by E0 equal to 2 eta 2 eta 1 plus eta 2. This is called the transmission coefficient. Okay. Is it okay? Are you getting the same expression?
Yes, sir.
And what about E2? Can anyone find E2 for me? Use E2 equal to E1 minus E0. E2 equal to E1 minus E0. And tell me what is coming. In terms of E0, not in terms of E1. I1 in terms of E0. In terms of E0, eta 1 and eta 2. Not in terms of I want E0. I want E2 in terms of E0, eta 1.
Sir, eta 2 minus eta 1 divided by eta 1 plus eta 2 into E0.
Right. Now tell me, where have you seen this type of equations before? This type of equation. Does it appear familiar to you?
A transmission line
Yes. And
in case of impedance.
and in this term, the transmission line, what is eta 2 minus eta 1 by eta 2 plus eta 1 called? Reflection coefficient, right? This term is also called reflection coefficient. So you can see the familiar, the similarity between this and the transmission line. This is called the reflection. Okay. So, okay, 5 minutes is remaining. Any questions? Yeah, there is just one or two small points which I will tell next. Any questions? There is oblique incidence also in the books, but I think that is better for BTech level. Oblique incidence means it is unlike the other case. Here it is like this. Here is my surface 1, surface 2, and it is like this. Okay, and how to find this? Same things, but here it is unlike here it was normal to the surface. Here it is not. If you want, we can discuss, but it is not. Okay, any questions? Any other questions? Let me take your attendance then.